In this video, I'll be teaching you how A-star algorithm works. We'll be going through all of the steps of the A-star and we'll be computing them also mathematically down on the paper or in your Notepad application. This video is part of my bigger series of my course. The link you can find in the description, where we'll create this RTS game you can see on the screen. If you want to get this RTS game, the link is in the description. There is also a link how to set it up. So get ready, this video will be longer. Let's start talking about A-star. Alright, so these are a grid, right? We are considering our map to be the green part here. This is the entire area here. So we have a 5 times 5 node grid because we have 5 rows, and for each row we have 5 nodes. In the previous lecture, we also explained Manhattan distance, and the Manhattan distance is applied where you want to compute the distance between nodes. So, for example, distance between this node and this node. So if you're not sure about the Manhattan distance, just check the previous video. Okay, now we are going to talk about how to choose the right path. When I'm looking at this, I know the right path will be like this, but my algorithm will be processing it differently. The algorithm will be assigning to each node. So in each node in our grid will be assigning following the metrics. Each node will have a G cost, H cost, and the F cost. And each metric will mean something else. So let's write it down so we'll not forget about it. Okay, here in the nodes.txt in our AI folder, we'll be writing all of our nodes. I will just remove this, we don't need it anymore. I'll just write here A star. Okay, and now. So each node will have a G cost, and the G cost is just a cost or the value from start node to candidate node. And what is a candidate node, I will be talking shortly after this. The H cost is the cost from candidate node, to end node. And F cost is just the both of them together. So this is a G cost plus H cost. Also, each node will have a parent from which the node originates. Okay, so parent, I don't need to write it now because you will see it when we will be writing it on the paper. Each node will have a parent. Okay, and then the Manhattan distances here are very important because when we'll be moving from node to node, we'll be using these values 10. It will be moving orthogonally, and 14 when it will be moving diagonally. Okay, so let me show you just a simple example how it could work. It will not be precisely working like this exactly. Just want to give you the rough approach, and then we'll go into detailed approach and we'll be computing everything mathematically. Okay, so as you see here, the starting node is this one here. Okay, and ending node is this one here. So we are starting from the starting node, from here. And we are considering all of the neighbors, where to go. So we can go 3 ways, right? We can go here, here, or here. So we can choose either this node, or this node. Of course, the algorithm can consider also this node, and this one node, all of the neighbors, but also this one. But you see, these ones are blocked. We are working only with this area inside here. So these nodes will be declining. We'll be not computing anything for these nodes because yeah, we don't need. There is a water, here is a sand, which is we cannot move on. So we are considering only these 3 neighbors. Okay? So now, for each 3 neighbors, we'll be computing these 3 metrics, G cost, H cost, and the F cost. It will be very important. So let's compute for now. Let's go very quickly over it. So G cost. G cost is the distance or the value from the start node to candidate node. So this is my candidate node. So we are moving on only one move orthogonally. So the orthogonal moves are for value 10. So G here will be 10. Okay. Here we are moving diagonal to get here. So the G cost will be 14 for diagonal moves. And here we are moving again orthogonally, so down. Orthogonal moves are horizontal or vertical. Diagonal moves are diagonal. All right. So again, G cost here will be 10. And then we'll compute the F cost. And the F cost is the distance from candidate node to the end node. Okay, and the shortest distance is always to consider the diagonal moves. So if you will consider diagonal moves from this node, you need to move 1 diagonal, 2 diagonal, 3 diagonal, and one orthogonal. So diagonals are for 14, orthogonal is for 10. So 3 times 14 plus 1 times 10, and this will get you the this is actually not the f cost, h cost, my mistake, this is h cost. So 3 times 14 plus 1 times 10. So this will get you value 42 plus 10, 52. Okay? So the h cost will be 52. So h cost will be 52, and the h cost. H 52, and the f cost is you just add them together, so this will get you 62. Again, and you're going to the next node, the next neighbor, this one here. So G we have already 14. We know the H, again, consider just the diagonals here. So 3 diagonals, 3 times 14 is 42, so this will be 42. And F cost will be, add them together, this will get you 56. And this node here, so H cost, again, consider diagonals first. So 1 diagonal, 2 diagonals, 3 diagonals, 1 orthogonal. So this will get you, again, value 52. And the f cost, add them together, 62. So now you will take on all of the neighbors and you will see which f cost is smallest. And you can see this one here is the node with the smallest f cost. So you will consider this as the next node, as the current node. And there is something called also open list and closed list, but I will not talk about it now. So okay, you will consider this node. So you have this here. And starting from this node, again, you consider all the neighbors where you can move. You can move here, you can move here, you can move here. So for all of these nodes, you're going to compute again G, H, and F. Okay, so what will be the G here? Okay, so that's the G from where you are moving here, this node, to the candidate node here. So that's a diagonal move, and they are costing 14. So the current node, which is a 14, plus diagonal move, which is 14. So 14 plus 14 is 28, so it will be 28. And then you're going to compute H cost, F cost, and so on. But I'm not computing it now because it will be doing on a paper soon. So I will just write here question marks. Okay? And again, for this node and for this node, again, you will compute the G, H, F, G, H, F. There are also some conditions where also these are your neighbor nodes. So you can also consider also them to be the next current node. So there are some cases when you want to recompute the G cost. And I'll explain it when we'll be computing mathematically. But for simplicity now, just consider these two. And when you will compute this, and I already know because I computed it, the lowest f cost will be this one here. So you will consider this as the active node. Okay? Now you can see there is everything is blocked here. This we have already computed. So what we'll do next? The one thing I didn't tell you yet, and we didn't mark it down, I will mark it down now, is that each node has a parent. Okay, we have talked about this here when I wrote it down. I did not write it down. Okay, so each node has a parent. So for example, when we computed these 3 neighbors here, we started here and we computed 3 neighbors, 1, 2, 3. All these neighbors, parent is this node from which each originates. So this is parent for this node, and for this node is this parent. Okay, then this was the active node, and we have computed the next nodes. So we have computed this one here, this one, and also this one here. So the parents are pointing like this. This is pointing to this one, this is pointing to this one, and this is pointing to this one. All right? Sometimes you can reparent in some conditions, and I will talk about this when we will be doing it mathematically. But as I ended up here, we are currently here. And we have considered everything. We have recomputed the G's, let's say. And again, we are going to consider the node with the lowest f. And from all these nodes you see here on your map, you can consider only this node, and this node, and this node here. Why? Because all the other ones are blocked, and these ones here that are in the squares have been already chosen. So you can go only from these 4 nodes, what you see. So you will choose the one with the smallest f. And you have multiple ones with the smallest f. So you have an f here, and here. So there are some conditions you can introduce, but I will just go for simplicity just to choose the first one. So this one. Okay. I'll just change the color here for a blue again. Like this. And I will remove this purple border here. Okay, so you will choose this one because this will be with the smallest f and is the first one. So this will be your current node now. Okay, and from this node you are going to recompute all of the surroundings, one that hasn't been chosen yet. So you can potentially recompute here G and here G and so on. But you will not do it because there are conditions will be not met. Doesn't really matter. So you're going to consider the next lowest f, and I already computed, so I know that the lowest f will be here. So this will be lowest f, and then you're going to again look at all of the neighbors, compute the GHFs, or recompute the Gs. And in this case, when the G is recomputed, here the G is 28, right? But this G was 28 when the path to this node was like this. That's when we have computed this G, 28. Okay, but now we are going from this node here. This is our current node. We are going here, G. So the G here is potentially lower. So G here is the one horizontal move, an orthogonal move. So G plus 10, this will be 20. So here now, when this happens, the G is lower, because we are going this way now, from this node here. We are not going this way. When the G is lower, you can reparent. You can see this is already pointing down here to this. But when this happens, that the G is smaller, then you can reparent. I don't know how to remove this arrow. Like this. Okay. Just get me the brackets back as we had them. Okay, so here you have recomputed a smaller G. So then you can change the parenting, and this was pointing before here. So when the G is smaller, you will repoint it here. Okay, and then you will choose the next nodes, and I'm not going through it. This will be this one for sure, this one, this one, this one, this one, and this one, and all of them they have a parent. So all of it point to the parents before. Okay, so this one is point here, this one here, this one here, this one here, this one here. So you have now a path. So you will just now look at the path from the end to the start, and you will just follow the parents, and this will get you the path like this. You see? So that's the entire algorithm. I know I went to the last parts, I went a little bit faster. It's a lot of mess here on the screen, but we'll be computing it now on the paper, so you will see exactly what's happening here. But just know this, that you need to just know how to compute the G's, H, and F's, and if you know this, then all of the algorithm is very simple. So now we are going to do it all on the paper, which will be fun. Okay, we'll build of computations, and this will take additional approximately 20 to 30 minutes. Okay, so let's pretend that we are algorithm now. Let me close this. And we'll go into our code. Okay, so computational part. I mentioned that you have something as the open list and a closed list. That's just a list, it's arrays. And currently they're empty, so I will mark it here. Create open list. Okay, so create open list. I'll call it OL. OL, and it will be empty currently. Okay, and create closed list, closed list, CL, and it's also empty. Now decide what's your starting node. So starting node, start node SN. Our starting node is the node 0, 0. 0, 0. Create the end node, that's your destination. Call it end node, EN. And this is your node 4, 4. Okay, when you look at the map, again, that's what you are having there. Okay, the next step, you will take a look at your start node and you will add it to the open list. So add start node to open list. So you will end up with something like this. Open list will be one node, which is 0, 0. And you are going to compute the GHF for the 0, 0 node. So for G, 4, 0, 0. And that's 0. Okay, because you're not moving at all. You are from starting node to this node is 0 moves. Okay, and the h cost from for 0, 0. So h cost is the distance from the starting node to the end node. So here, all right. So from the start node here to the end node, and that's for diagonal move. So that's a 4 times 14. Okay, so that's the 56. If you want to have it mathematically, I can see, look at the map and I can see it, but if you want to do it mathematically, then it will compute the distance x. Okay, so you want to move from where? You want to move from 0, 0, and you want to move to 4, 4. So you will compute the distance x, dst x, and that's equal to, in absolute value, 0 minus 4 plus, oh, actually that's it, that's 4. Okay, and then you will compute the distance of the y, and that's in absolute values, the same 0 minus 4, and this will get you 4. Okay, because you're getting x's from one coordinate, so 0, this 4, that's for the x distance, and here 0, and the 4 from the other coordinate. 0 minus 4, 0 minus 4. Okay, distances. Now you check this formula for the Manhattan distance. If the distance x is larger than distance y, it's not, because they are the same. So you're going with this formula, 14 multiplied by distance x plus 10 multiplied by the distance y minus distance x. So when you will add this full formula, so distance, or I can call it h, equal, so 14 multiplied by the distance x, so that's 4, this here, plus 10 multiplied by the distance y minus distance x, so that's a 4 minus 4, that's 0. So the set is 56 together, so is equal 56. Okay, so h for 0, 0 is 56. So the f for this is a 0 plus 56. The g plus h, so it's a 56. Okay, and you have it on open list. So this open list here, you have a 0, 0. So now you choose the node with the smallest f from the open list, and you will add it to the closed list. Okay, so now you will, again, open list will be empty because you remove it from open list, and you will add the 0, 0 to closed list, CL, closed list, and you will have there 0, 0. Okay, and now you are going to compute all of the neighbors for 0, 0. So all of these 3 nodes that are surrounding here, this node, this node, this node, and you're going to compute f, you're going to compute g, h, and the f. Okay, and when the node has been added also into the closed list, it's cancelled as a currently active node. Okay, so currently active node is 0, 0. That's the current active node, the last chosen to the closed list, 0, 0. Okay, so you're going to choose all the neighbors for 0, 0. Okay, neighbors I will just write into like this in between on these dashes. So the first neighbor, what is the neighbor? So what are the coordinates here? This is 1, 0. So this is a neighbor 1, 0. This is a neighbor 1, 1. And this is a neighbor 0, 1. Okay. So first, let's start with the neighbor 1, 0. Okay. You will also set parent. And the parent to this node is your active node from which this originates. So this is 0, 0. So parent, set parent to 0, 0. Okay, and you're going to compute the g now. So g for 1, 0. Okay. Okay, and what's the g? From here we talk from a 0, 0, right? So from 0, 0, we are going 1 horizontal, so orthogonal move is a 4, 10. So the g here will be 10. G will be 10, or you can use the Manhattan distance formula, just replace the numbers and you will get 10 anyway. But yeah, that will be faster this way. So g is 10. The h for 1, 0. Now you could use the Manhattan distance. So you could compute distance on the x and distance on the y, and you could compute the Manhattan distance. So here you are going like this. So you're computing the distance x, and the distance x will be 3, and distance y will be 4. Okay, why is that? Yeah, let me write it. So we are going from 1, 0, to where? To 4, 4. We are going to the current candidate nodes, 1, 0 to the 4, 4, which ending node. That's the age what we are computing. So here we have x1, y1, x2, y2. Distance x, dst x, is x1 minus x2 in absolute values. x1 minus x2. And this will get you 1 minus 4. And this is equal to 3. Here we have 3. And distance y is the same in absolute value. That's a y1 minus y2 in absolute values. That's the 0 minus 4. Okay, 0 minus 4. And that's in absolute values is 4. So that's your distance y. So that's you will be always computing it this way. Okay. That's why the distance is x3. Distance y is 4. Again, you will look up here, this formula, and you will see if the distance x is larger than distance y. It is. It's not. Y is larger than x. So you're going with this formula. 14 multiplied by the distance x plus 10 multiplied by the difference between the a distance y and distance x. Okay? So now when you will replace it to the formula, you'll get h equal 14 multiplied by distance x, so multiplied by 3 plus 10 multiplied by 1, because 10 multiplied by the 4 minus 3, distance y minus distance x. Look here. 10 multiplied by the distance y minus distance x. So 10 multiplied by 1. And this also means when you're looking at this, so to get to the end node, you need 3 diagonal moves and 1 orthogonal move. So that will this value will get you, that's 28, 42, 52 together. So the h here will be 52. Okay? And the f here for 1, 0, 1, 0 will be this 10 plus 52, g plus h. This is 62. Okay, and I will be going faster now because I don't want to spend here a million hours. Now we're going to consider the next neighbor. Neighbor 1, 1. Again, we'll set parent to 0, 0. We are going to compute the g for 1, 1. And the g for 1, 1 is what? From the current node 0, 0, active node, to 1, 1. What move we need to do? Again, looking here. It's one diagonal move down here, so it's 14. So this will be 14. Okay, now the h for 1, 1. If we will compute it into the formula from the 1, 1 to 4, 4, you will get the distance x and distance y to be 3. So distance x is 3, distance y is 3 as well. When you will replace it to the formula, h, this will get you 14 multiplied by 3 plus 10 multiplied by the 0. So this means 3 diagonal moves and 0 orthogonal move. And this will get you together 42. 42. So now we're going to compute f for 1, 1. And the f for 1, 1 will be 14 plus 42, and that's 56. Perfect. Now the next neighbor, and that's the last one, for 0 and 1. Set parent to 0, 0. That will be the same. Now we are going to compute the g for 0, 1. Again, we are going down. If you look at the map, we are going down, straight down. Here is this. So that's the one orthogonal move. That's for 10. So the g 0, 1 will be 10. Now when we will compute h for 0, 1, so from 0, 1 we're going to 4, 4. This will get you again 52. If you will replace everything, distance x, distance y, and to here, you will get 52. Okay, from 0, 1 to 4, 4 will be 52. You can do it. You can compute it on the paper if you want. Okay? Or okay, that will be the last one I will be computing this video. So we are going from 0, 1 to 4, 4, and you compute the Manhattan distance. So distance x will be 0 minus 4, that's 4, and distance y will be 1 minus 4, that's 3. Okay, so I'll just replace it here. Distance x is equal to 4, and distance y is equal 2, 3, as I said. Okay, just other way around, as you see here. Okay, so now this will get you, if you represent the formula for an h, it will give you 14 multiplied by 3 plus 10 multiplied by 1. Okay, 3 moves diagonally, 1 moves orthogonally, and this will get you value 52. Add them together to get f for 0, 1. 10 plus 52, this will get you 62. Now when you have computed all the neighbors, you will add all of them to open list. Add all neighbors, and I never know how to spell neighbors, so maybe like this. Add all neighbors to OL, to open list. Okay, so what we have now in open list? Open list equal, so all of them are now in open list. 1, 0, and 1, 1, 1, 1, and 0, 1 are all in open list. Currently, what we have in a closed list? In the closed list, we have currently only 0, 0. That was a bit added to the closed list before. Okay, so when all of the neighbors are computed, that's our current status and been added all of them to open list. Now we are going to choose one from open list to the closed list, and this will be your active node. So you are choosing the one with the lowest f, and that's 1, 1. So you will remove it from the open list and add it to the closed list. So I will get it from here. I will get this 1, 1, or actually I will just write on a new line. So here will be choose one with smallest f and move it to closed list. So current status will look like this. Open list will be 1, 0 and 0, 1, and your closed list will have already 0, 0 and it will have 0, 1. Not 0, yeah, and 1, 1. 1, 1. So that's your current status. And your active node will be 1, 1. So choose 1, 1 as active node. And for the active node, you are going to examine all of the neighbors now. Okay, so again, we are going now look at the 1, 1 here and examine all of these neighbors here around. Again, let's do it mathematically. So the first neighbor, okay, will be 1, 2. Okay, well, 1, 1, so 1, 2. So we'll now set new parent. So set parent, 1, 2 parent will be 1, 1 because that's our currently active node. So the parent will be 1, 1 to the 1, 2. Okay. And again, you're going to compute the G's. So G, 1, 2. Okay. So what is a G, 1, 2? So that's your parent's G of the 1, 1 plus the type of the move you need to go. So if you're going from 1, 1, so from here, and you're going where? You're going to 1, 2. Where is 1, 2? 1, 2 is here. So you're going to here, right? So you're going from here to here. That's orthogonal move. You one down. So plus 10. Okay. So what was the G of 1, 1? From where we are going. So when you look up here, G of 1, 1 was 14. We have it here. Okay, so this will be 14 plus 10. So I can write as a formula. G of 1, 1 plus orthogonal move. It's equal to 14 plus 10, and that's 24. That will be your G. Now we're going to compute H again. So you're going from 1, 2 into 4, 4. Again, remember H is from the current node, from the neighbor we are computing now, to the end node. Okay, and the G is just from the active node to the current neighbor, to the candidate node, as we wrote it. Okay, so if you compute the H, I'll just write the numbers. You can do it on the paper, but if you want to compute the H for this one, it will get you 38. Okay, and the F for 1, 2, therefore will be 38 plus 24, and that's 62. Okay, now we're going to compute the next neighbor. Just copy that upper line. So next neighbor will be for 2, 2. Okay, you will set the parent to 1, 1. Okay, so again, G for 2, 2. This will be the G of, I'll write it down. This will be G of 1, 1 plus type of the move. So basically now we are going from 1, 1 to 2, 2. So from this node here, there's active node 1, 1 to the day's neighbor. So that's a diagonal move. Okay, so that's the G of this node plus type of the move. Okay, so let's compute it. So that's a diagonal move. And we know that G of the 1, 1 is 14. So plus 14, and that will give us 28. Now the again H for 2, 2. This, when you will compute this, this will get you 28. So F for 2, 2 will get you 28 plus 28, and that's 56. Okay. And then now the next neighbor. Okay, so neighbor now to 0. You will set parent to 1, 1. And it will going to compute G for 2, 0. 2, 0. So as we know, we are originating from 1, 1. So G of the 1, 1. And we need to go diagonally. Diagonal move. Why diagonally? Because look at here. We are on the 1, 1. So we are here. And to 0, that's a neighbor. We need to still compute here. So that's the one diagonal move up here to get there. Okay, so that's the 14 plus 14, and this will give me again 28. I'll cause the H cost from the for the 2, 0, so from 2, 0 to 4, 4. When you add it to the Manhattan distance computation, this will get you 48. Okay, and total cost for F for 2, 0 is 48 plus 28, and this will get you together 76. Okay, so let's look at this now with their current state. So we have been, that's an active node here, 1, 1. And we have computed 2, 0, so we have computed F, G, H for this one, and for this one. So for 2, 0, 2, 2, and for 1, 2, right? Look at this. 1, 2, 2, 2, 2, 0. All of them are computed here. This we are not considering as a neighbor. This is blocked. This is blocked as well. However, what about these ones here? What about these ones here? This one here, that was the last. That's in a closed list already. 0, 0 is in a closed list. When you look at the closed list, that was considered. It was an active node before. It's in the closed list already. So we are not considering this. That's already out of the picture. We are not doing anything. But this here, we can compute. We can recompute the G's actually, because the G's were computed from the before active node, which was this one, to this one, and here. That was the G's. Okay, but now we are computing this path here, this and this. So the G here will be this G plus type of the move, this G plus type of the move. So potentially we can update these two nodes here. And now comes the computation, which I didn't tell you before. Okay, because now the G's will be different. It can be recomputed. Okay, so let's take a look at this. I'll just revert this. Get back to the code and let's consider these parents. Okay, so the parent of this 1, 1 node is also what node? 0, 1 node. Okay, and the 0, 1 node is already on open list. It's open list in open list or in OL or already in OL. It has parent. It has parent 0, 0. Okay, let's take a look at this. We have computed already 0, 1. You look at here 0, 1. That was the one of the first nodes we have computed 0, 1. We have set parent to 0, 0. That's because that's originated from the 0, 0, and that's all of the information. We have computed G, H, and the F. And we have added it to the open list, so it's already in open list. See? So now we can potentially recompute it. Okay? So what about the parenting? Because now the current active node is 1, 1. Remember, we have chosen the 1, 1 here as the active node. But this node has a parent 0, 0. So should we reparent to the 1, 1? So what about parenting? All right, parenting, set it to 0 to 1, 1. All right, Not yet, okay? Because first we need to compute candidate or tentative G, okay? So first compute new, or you will rather call it in these terms, or tentative G for 0, 1. For 0, 1, okay? Because the 0, 1 has already G cost. Okay, that's very important. Okay, I'll just make it wider. Okay, 0, 1. Because 0, 1 has already parent and G cost has already G cost. Okay, so what we are going to do, we are going to compute the tentative G. So TG, I will call it TG for 0, 1. And this will be G of the current active node 1, 1 plus type of the move to get to 0, 1. If you look at the map, this will be orthogonal move plus orthogonal move. Okay, look at this. When we computed the G for 0, 1 up here, one of the first nodes we have computed here, 0, 1. Before the active node was 10. So we went from, I could write it here, we went from, okay, so G of 0, 0, that was the current active node before, active node is 0, 0, plus type of the move. So from the 0, 0 to 0, 1 to the orthogonal move, and that's equal to 10. That's why we got the 10, because we went from 0, 0 to 0, 1. And now we are in a 1, 1. So we are going this way. Okay? So that was the before it was 10. Okay? Because the G of 0, 0, 0 is 0 plus move plus 10. 0 plus 10 is 10. Okay, so now we're going from 1, 1, going straight up. Okay, straight up to 0, 1 is here. So we are here, this active node. We are going up, straight up, that's 10. Okay, so G of the 1, 1 plus orthogonal move. G of the 1, 1. Look at what is the G of 1, 1. Okay, so G of 1, 1 is 14. That's what we've computed here. Okay, it's 14, so that's a 14 plus orthogonal move. That's 10. Okay, and this will get you 24. That's its tentative G. Okay, and now what are you going to do? Compare tentative G of 0, 1 with existing G 0, 1. Okay, so what's that? Tentative G, what we have now computed, 0, 1, is equal to 24. Okay, the G that already existing on this node, 0, 1, is 10. That's what we have looked up there. Now we will compare it. Is tentative G larger than the current G? So is the tentative G larger than the current G? So is 24 larger than 10? Question mark. It's not. 24, oh, actually, 24 is larger, okay, than G. Okay, so in that case, you are not action needed, okay? So if the tentative G is larger than the current G, then no action is needed, okay? So what's the resolution of this? Tentative G is larger than the current G, so no action needed. So we don't need to do anything, okay? So we just completely ignore it. We will keep the G's and the parenting as it was before. Okay, so we have now compared this tentative G with the existing G. We have discovered the tentative G is larger than the current G, so we don't need to update. Okay, so no action needed. Okay, so now the next neighbor. Okay, remember, just keep a track of this, where we are currently. We are still on 1, 1, right? Now we have computed 0, 1. So this one here, we have discovered that we don't need to recompute it because the tentative G is larger as the G, but there is a next parent here. Okay, so this is this 1, 0 parent now. So we are trying to find the tentative G for here. Before, when we computed G, we already have this on open list. We was from this node, but now we are from 1, 1 is our active, and we want to compute now tentative G for here. Okay, I think I was explaining it the other way around. I was talking about the 1, 0 but I thought it's the 0, 1, but doesn't really matter because they are anyway orthogonal distance, so it doesn't matter. The formula will be still the same. Okay, so yeah, let's continue now. I will copy this line, so we are going again to inspect the next neighbor, and the next neighbor will be just 1 and 0. It's already in open list, and it has parent 0, 0, because that's what we have computed. If you look at it up here, 1, 0, here, one of the first one, when the active node was 0, 0, we have computed here. We have all this G, 10, we have H, we have F, everything. So now we are going to compute the tentative G, but tentative G from now originating from 1, 1. So let's write here TG for 1, 0 equal of G of 1, 1 plus orthogonal move. Orthogonal move. Okay, and this is equal, so G for 1, 1 is 14 plus orthogonal move is a 10, and that's 24. Okay, so now we know that TG for 1, 0 is equal to 24, and all the G for 1, 0 was only 10. So now we can see that 24 is larger than 10, so therefore no action needed. We don't need to update anything, and there are no other neighbors to evaluate. So now we can add these neighbors to open list. Okay, so how our open list currently looks like. I need to scroll up to see the open list and close list. So that's our current open list and close list. So all these neighbors now we have been evaluating, computing the F cost for them. We need to add to open list, and these two ones here, 0, 1 and 1, 0, they are already in open list, so we don't need to add them. You see they are already in open list. So only these three, right? So 1, 2, 2, 2, and 2, 0. Okay, so 1, 2, 2, 2, and 2, 0 are added into the open list. Okay, and you can write it down also, so you know. Here add neighbors to open list. Add neighbors to open list if they are not there already. Okay, so all these three has been added, and then again choose the one with the smallest f. Choose the node with smallest f. If you would look at all these nodes, you would discover that the 2, 2 has the smallest f from all these nodes. So the next node will be 2, 2. So move 2, 2 to close list and set as active node. Okay, so you are moving 2, 2 from here to close list. So this will now come to closed list, and your open list will be now without 2, 2. Okay, so that's your current structure. This you have an open list, and this you have in a closed list. Okay, and the active node is 2, 2. Okay, and now you are going to compute all of the neighbors for 2, 2. So you look here, you look at the 2, 2. Where is this? Here is a 2, 2. And this will be not much work because here all of this is blocked. So here we need to just consider this node. And this node we already computed. This is node 1, 2. And it is already neighbor 1, 1 because we have originated from this active node before. Okay, so if you look on the node 1, 2, we've already computed it here and already has a parent 1, 1 when the active node was 1, 1. So now we need to just look at the tentative G from this node the same as we have done before. Okay, so that's the only neighbor we need to consider now. So these two dashes here, and let's write here we are choosing the neighbor 1, 2. Okay, it's already in open list. In its, how we wrote it. I will just copy this line. Already in open list, it has parent 1. It has parent 1, 1. So we are going to compute tentative G for 1, 2, and that's a G originating from 2, 2, plus what kind of move we need to do from 2, 2 to 1, 2. You see it's orthogonal move, so plus 10. Okay, so G 2, 2 plus orthogonal move, and the G of 2, 2 What was the g of 2, 2? We need to go up here, see the g of 2, 2 was here, was 28. Okay, so that's a 28 plus orthogonal move, which is value 10. Okay, I hope you're having fun to computing it, but I just want to make sure you understand it. And if you're already familiar with this, you can go ahead, you can just make it faster, this video, or you can skip it. Okay, and now we have a TG for 1, 2 is equal to 38, and the old G for 1, 2, do you remember what was it? I don't remember, so I need to just look it up here. So for G for 1, 2 is 24. Okay, so G for 1, 2 was 24. So therefore 38 is larger than 24. So no action needed. No action needed. Okay, so there are no other neighbors to evaluate. Okay, so from 2, 2, because it was the only neighbor and all of the path was blocked. So no other neighbors to evaluate. Okay, so we have checked already all of the neighbors. We have updated what we could. Everything else is blocked. So at this stage, we are looking to the open list and looking for the new active node. So I will copy this over down here. So their current stage. The Fs here, if you don't remember, the first 3 nodes here are 62 and the last one is 76. So we can just choose something from the first 3 ones because that's the lowest F. If you don't know what to decide from the 3 to choose from, just go with the first one. So yeah, we are going with the first one. So I will write it 1, choose the first with lowest F. Okay, which is 1, 0, and move it to close list, and move it to close list to CL. Okay, so we are going to 1, 0, and moving it there, up, moving it there, close list, and this one here I will just copy over down so we can also have the current stage of this. We have removed 1, 0 and moved it to the close list. So that's our current stage of the close list, and also select the 1, 0 as the active node. Active node is 1, 0. Okay, so when you will look at your map to see it visually, 1, 0. So we are choosing now this active node. Okay, 1, 0. And from this node, we are going to now inspect all the neighbors. So you see here the neighbors is, we can decide this is blocked, so no, and this. And all of them we already computed before, and they have different parents. So let's take a look at what it will look like. We'll start with this one here. So you can see this is the orthogonal move to go to this neighbor 2, 0. This is the 2, 0, 1 location. And 2, 0 has already parent. If you remember, when we have the 1, 1, before the 1, 1, this one was active, we have computed this neighbor here of 2, 0. So we have here for sure the G, and the parent of the 2, 0 is already 1, 1. Okay, so let's continue in this. All right. So to dishes that we are choosing the parent. So now choosing the neighbor, and the neighbor here is 2, 0 now. It's already in open list, so we'll copy this line. Here is already in open list, and it has parents 1, 1. That's correct. So we are going to compute TG, tentative G, and for 2, 0, and that's equal G over active node 1, 0, plus we said orthogonal move, and that's equal G of 1, 0. Do you remember what it is? If you don't remember, G of 1, 0, that was the one of the first one computed. So that's the G of here, up here it's a 10. Okay, I'll scroll down back here. Okay, so that's a 10 plus orthogonal move plus 10. This is 20. Okay, so TG is 20. So let's write it down. TG of 2, 0 is 20, and all the G for 2, 0, we need to look it up. So let's find here 2, 0. Where you are here, 2, 0. So the old G is 28. Interesting. Now we are getting into interesting situation. So that's a 28. Okay, let's write it down. So G of 2, 0 is 28. So now we are in a situation that here the TG is smaller, not larger as before, but it's smaller than 28, so the active G. So now the action is needed. Okay, so action needed in this case. So if it's smaller than TG, then we need to update the G cost and the parent. So update G cost and parent. Okay, so we are going to update G. So update the G of to 0 to 20. Okay, it was before 28. As we see here, it was 28. Now the TG was, we computed through the new path 20, so update it to 20. Okay, and recalculate F. Recalculate F. Okay, so now the F will be what? F for 20 is equal to new G, so new G for 20 plus H for 20. H will stay unchanged because we are still the same distance from the end node, but then the G is the new, so 2 plus, and what was the H for the 20? We need to go up here and see what was the H for 20. Okay, here, H for 20 was 48. Okay, so H for 20 was 48, so now the new F is 68. I should mark it here, up the G cost, also F cost. F cost and the parent, so that's a 68. And now we are going to update parent. Update parent to 10. Okay, because from now we are going there. The 10 is our current node, that's our currently active node here, our current node. So they'll also be able to update parenting. So the parent is not any longer 11, but rather 10 for this node. So update parent to 10. Okay, so that's done. So we can also recalculate the other neighbors. So we have been done this. So we need to recalculate also this neighbor. This actually not, because that was already active node, so we cannot. So we can actually calculate also this neighbor, but there will be no action needed. I already tested out. I computed tentative G and it was larger, so there is no need for recomputation. I done it outside of the lecture, but if you want, you can compute it. But it's already taking, like, we are spending here a lot of time. So you can go with this computation until you will reach the end node. Okay, so I'll just finish it up very quickly. Okay, so what would you do next here? From this point on, you will update all the neighbors, as we always do. Update or check all the neighbors. You don't need to update the necessary. Just check all neighbors. Okay, then if you checked everything, just choose the next active node. Choose the next active node and move it to close list, and do this until the active node or current node, whatever you want to call it, until active node or current node, active node is not equal end node. Okay, when the active node will be same as the end node, so you reach the end, then you will stop this and you have found the way. And when the algorithm is correct, and you will do it at home after on the paper, or maybe you don't want to do it because it takes some time to compute this, because we do it anyway programmatically, you should end up with such a list. This will be your closed list. Okay, so closed list. Final stage closed list. Final stage CL. Okay, this will be your final stage closed list. These first coordinates, sure, we don't need to display this anymore. Okay, so these ones are the parameter, that's your nodes in the closed list, and that's their parents. That's their parenting, okay? So that's the actual nodes which are in a closed list. I just marked here so you know what are the parents of these nodes when they get updated. So this here in the blue, that's what you should end up in the closed list. And you can see the last node in the closed list is 4,4, which is your end node. So you do it until you find the 4,4, and that's what we have found. And then to find the path, you are just going from the end. So you're starting with an end node, like this, okay, 4,4, and then you go. The next node in the line will be your parent. So 4, 3. Okay, so then is 4, 3 is the next node in the line. Then you look at the 4, 3 here and check its parent. That's 4, 2. So the next node in the line will be 4, 2. 4, 2. Okay, and then I check the 4, 2. And then parent is 4, 1. So you will get over with the 4, 1 is the next node. Again, you will check, where is this? You will check the 4, 1. And the parent is 3, 0. So you will go with the 3, 0, the next node. 3, 0. All right, and then the parent of this is 2, 0. So 2, 0 is up here, you can see. It's not the next one, but the 2, 0 parent is here. So 2, 0. 2, 0. All right, and the parent of 2, 0 is 1, 0. So again, skipping all of this, and that's 1, 0 here. 1, 1, 0. And the parent of 1, 0 is finally 0, 0. So you have found it. So 0, 0, 0, that's your path. And now we just need to revert it. So you will go other way around. That will be the path to the end. Just revert the end. So 0, 0. I'm just going to revert it, okay? 0, 0, 1, 0, then 2, 0, then 3, 0, 3, 0, then 4, 1, and then 4, 2, and then 4, 3, and then 4, 4. And you have found a path just like this. That's your final path from the start to the end. So let's take a look at this and let's verify it. And I just already, okay, here it is. So look at this. Starting 0, 0. That's here. Okay. Then is a 1, 0. 1, 0 is here. Okay. 2, 0, 3, 0. 2, 0, 3, 0. Then 4, 1. Skipping this, you can see because you can move diagonally here. So 4, 1. That's this one here. And then this will be 4, 2, 4, 3, 4, 4. 4, 2, 4, 3, 4, 4. And we are in the end. So you can see that's the final path. And that's how you implement A* algorithm. Hopefully, now you got an idea how we computed it. Remember, always look at the active node and choose all the neighbors and compute G cost, H cost, and the F cost. And all of them are added to the open list. From the open list, choose the smallest f. If we have multiple smallest f, choose the first smallest f, add it to the closed list. This will become your active node. And again, recheck all the neighbors. If these neighbors are already in open list, check the tentative G. And if the tentative G is smaller than the current G, then you are going to update it, the G, then you update the F cost, you will change the parenting, and then you will check all the neighbors like this. Again, you check the open list, choose the smallest f, put it to the closed list, select the active one, and like this you are iterating until the node, in the last node, what you will find, the active node you will choose, will be your end node, as in this case. And then you stop the iteration, finito, all done, and you will just get this path. You will follow the parents. Okay, this will construct you the path, and then you just revert it, and this will get you the path from the beginning to the end. And here you have it. And this lecture was extremely long, I must say. Okay, hopefully you survived, and now you have understanding how we are computing it. Look at these steps. Everything you can find in the description. Any questions, ask in the discussion, and that's gonna be it for this video. And the next one will be applying these steps programmatically, and we'll be doing it in the code so we can actually move the unit to the end. Okay, and avoid obstacles. Okay, so for this, I see you next lectures. Cheers.